In this video, I'll be covering the solutions to practice quiz 5. Before we go there, though, I would like to patch something that I didn't cover as thoroughly as I would like. I have amended the notes for the review, and I will cover them, the additional piece here on center of mass. So suppose I have two masses on the x-axis. One has mass m1 at position x1. The other is mass m2, position x2. Then the center of mass of the system of two masses is going to be m1 times x1 plus m2 times x2 divided by m1 plus m2. That's the center of mass x-coordinate. Now, if we let m be the total mass of the system, capital M, then I can write this as 1 over capital M times m1 x1 plus m2 x2, replacing the m1 plus m2 by capital M. Okay, so by the way, we can do similar steps to get the center of mass velocity if we're just averaging the velocities out, getting the weighted by the masses. So you do m1 v1x plus m2 v2x divided by 1 over m. That will give you the velocity of the center of mass. And the way you would derive that is just by taking the time derivative of both sides. Time derivative x gives you v cm. Time derivative of x1 gives you v1. Time derivative of x2 gives you v2. If you take another derivative, you can get the center of mass acceleration. So if I take the derivative, I get the acceleration of the center of mass. 1 over capital M times m1 a1x plus m2 a2x. Use this acceleration of particle 1 plus the acceleration of particle 2. So the structure is very simple. You just weight the quantity you're measuring by the weight, by the mass of the particle. So m1 x1 plus m2 x2 and divided by the total mass. You weight the velocity with m, the masses. So you get m1 v1x plus m2 v2x divided by capital M. And then for the acceleration, it's m1 a1x plus m2 a2x divided by capital M. So the reason these are useful is that you can show that if you have a net force on the system, the sum of all the external forces on the system, then the F net in the x direction is the total mass, m1 plus m2, times the acceleration at the center of mass in the x direction. Okay. Now, as a result, if the system is isolated and there's no net force on the system, and the center of mass xm is initially stationary, so then in that case, it remains at the same point for all time. Okay, so if I have two masses like this, and the center of mass is right here, and they just pull on each other, then the center of mass always remains there, so that if they're pulling on each other, they will meet at the center of mass, which will be the same as the initial position of the center of mass. Okay, so now we'll get to practice quiz 5. So I should mention this practice quiz has problems that are more difficult than the actual quiz. So my advice to you as I go over the solutions, I will try to emphasize the pieces of the solutions, noting that for the problems on your quiz, there won't be so many pieces. But the point I'm trying to make is each piece you should be able to understand. Maybe the synthesis of putting together 3 different pieces in one problem is maybe a bit difficult, but I would like you to understand how each piece, the concept behind each step. Okay, we have 3 spherical masses are located in a plane at the position shown below. 0.3 kilograms for Q, 0.5 for R, 0.6 for S, and we want to know the moment of inertia of the 3 masses with respect to an axis perpendicular to the xy plane and passing through x equals 0, y equals minus 2. So x equals 0 is this line here, minus 2 is this line here, so that's this point. Since the masses are of a small size, you can neglect the contribution due to moments of inertia about their centers of masses. Okay, so we want the moment of inertia about this rotation axis. So we need the distances of these particles from this rotation axis. I need this distance, I need this distance, and I need this distance. Okay, So I can get these distances by reading off the number of blocks I have here. Okay, so for R sub capital R, this point R here, I have 1, 2, 3, 4, 5, 6. 6 blocks here. So what I'm doing is I'm getting a right triangle. I'm going to get the hypotenuse of the right triangle. So I have 6 here. That's 6. This one will be 1, 2, 3, 4, 5. So I have square root of 5 squared plus 6 squared, or square root of 61. Later on, I'm going to actually square this distance, so I'm going to just leave it this way. For RS, this distance is going to be 3 blocks. This is 1. So I get RS is square root of 3 squared plus 1 squared. That's the square root of 10. Then I have, for RQ, I have 1, 2, 3, 4, 5. This is 5. This is 2. So I have square root of 5 squared plus 2 squared. And that's square root of 29. So to get this moment of inertia for a particle with respect to a rotation axis, the formula for a particle is mr squared. For a simple particle, I is equal to mr squared. So I'm going to do that for each case. I have mqrq squared, and that's, okay, I'll just go on. And then I have mr r squared plus ms rs squared. And then I plug in the values. 0.3 for mq, 29 for r, 29 square root for rq. So I will square that, get 29. For mr, I have 0.5. And for rr, I have the square root of 61. So squaring that gives me 61. ms, the mass is 0.6. And the rs is square root of 10. So squaring that gives me 10. Add these together, I get 45.2. And the units for moment of inertia is kilogram times meter squared. Okay, so the basic steps are I have mr squared for the moment of inertia about this rotation axis here, and the particle located here at a distance r with a mass m. And we add the moments of inertia together. Okay, next problem. I have a thin rod, so the reason I know it's thin is they don't give any dimensions here, so you neglect the width and the thickness of this rod. A rod of length L equals 1.05 meters, has a mass of 1.2 kilograms, and is rotating as shown at 650 revolutions per minute. How much kinetic energy is associated with its rotation? Okay, so let's take a look at the rod first. We know we're going to need the moment of inertia about the center of the rod. Okay. And so that's 1/12 ml squared. That's on your equation sheet. So we have 1/12 1.2 times the length 1.05. Square that, and then I get, multiplying these together, 0.110 kilogram meter squared. The kinetic energy of rotation is 1/2 I times omega squared, where omega is the angular speed or angular velocity, magnitude of angular velocity. So we're given it in terms of 650 revolutions per minute. So I have 650 revolutions divided by a minute. But now the revolutions are 2 pi radians, and the minutes is 1 minute is 60 seconds. So I have 650 times 2 pi divided by 60 gives me 68.1 radians per second. Now then the rotational kinetic energy is 1/2 I, which is 0.1 times omega squared, so 68.1 squared gives me 255. Okay, so the concepts here are twofold. One is getting the moment of inertia of the rod, so you have a 1/12 ml squared. Then we have to use the formula for the kinetic energy of rotation, 1/2 I omega squared. And then there's an additional step, and a secondary step here, that you have to convert omega from revolutions over minutes to radians per second. Okay, a revolution is 2 pi radians, and the minute is 60 seconds, and then you flip that together and you can get the rotational kinetic energy. Okay, next part here. Next question. M here is a solid cylinder with mass 2.15 kilograms. The radius r is 0.05 meters, and it pivots on a thin, fixed, frictionless bearing, so just this little axle here. A string wrapped around the cylinder pulls downward with a force F, which equals the weight of a 0.710 kilogram mass. In other words, F is equal to 6.958 newtons. Calculate the angular acceleration of the cylinder. Okay, so we pull down with the force here, and so we can calculate the torque, all right? So for all these quiz problems, when we have a force, we're going to probably have to calculate some torque, okay? So torque is R cross F. The magnitude of the torque will be R times F times the sine of the angle between them, the sine of the angle between them. Here's my R vector, here's my F vector. I extend the R vector, the angle between the R and the F vectors is going to be 90 degrees. So it's R times F times the sine of theta is equal to 1. So I get R, which is 0.05, times F, which is 6.958, it's given. You get 0.348 Newton times meters. So that is the calculation of the torque. But now we need to connect it to the angular acceleration. So then we have tau net is equal to I times alpha. That's on your equation sheet, but you can just remember that as being the rotational version of Newton's second law. Instead of F net is equal to ma, you have torque net is equal to I alpha. Okay? So now I can solve for the angular acceleration. It's the torque net over I. So now the moment of inertia for a solid cylinder is the same as the disk, but it's 1/2 mr squared. Okay. So now we have the net torque is 0.348 divided by 1/2 mr squared. You get 129 radians per second squared. Okay, so the concepts here are we have a force, we need to calculate the torque. So the torque is R cross F. The magnitude of the torque then is R times F times the sine of the angle between them. The angle between them is 90 degrees. So here's R. So in order to calculate the angle, you should make R's, well, you can draw R again here, and so that it starts from the same point as F does, and you can see that the angle is 90 degrees. Okay, so once you get the torque, you can write down the analog of Newton's second law. For rotations, torque net is equal to I omega, right? And so now I can solve for the angular acceleration. This guy's angular acceleration. I get torque net divided by I. So then I get 0.348 divided by I. But another concept here is that the moment of inertia of a disk or a solid cylinder, a uniform disk or a solid cylinder, uniform cylinder is 1/2 mr squared. Plugging in all the numbers for the mass and the radius, you get 129 radians per second squared. Okay, moving on. This problem is a hard problem. So again, this is harder than what we would probably put on a quiz, but let me try to break it down into pieces so that each piece you should be able to do. Okay, so altogether this problem is probably too hard, but each piece you should try to understand. Okay, the question is, if instead of a force F, instead of just pulling on it with your hand, you actually attach a mass that has a mass 0.710 kilograms, the question is, what is the angular acceleration of the cylinder? Okay, so now what we're going to do is we're going to try to convert this. So I mentioned this in lecture a couple of days ago. We're going to convert this into this sort of Atwood problem where we have one mass on a frictionless horizontal surface and have another mass that's hanging like this. So in other words, this cylinder is going to spin like this mass moves. In other words, the angular acceleration of this guy will be similar to the acceleration of this mass. Specifically, the angular acceleration times r will be the same as the acceleration of this mass. But I need to figure out what what kind of a mass, or what the effective mass will be of this hypothetical linear problem. Okay, I'm converting this problem into this problem because I know how to solve this problem very fast. Okay, so what I'm going to do is, again, this part is kind of complicated, but hopefully you can follow the steps because each of the steps you should know. Okay, so let's try to find the equivalent linear F net equals ma behavior. So we're going to pull on it with the force F and figure out if I have an acceleration A. Okay, what is the effective m that I'll get? What is the mass that I would get? Okay, so I pull with a force F. The torque will be R times F times the sine of 90 degrees. Sine of 90 degrees is 1. But the torque, again, just like we had up here, the torque is going to be equal to I times alpha. That's Newton's second law for rotations. But alpha is A over R, so that's, I'm talking about the tangential acceleration of the point on a rim. Okay? A is this tangential acceleration. The reason I don't care about the centripetal acceleration is I'm actually interested in what is the acceleration of a point in the straight part of the string, not what's going on around the rim. I'm interested in what's going on in the straight part here, and that's only going to be the tangential acceleration. Okay, so if you want, you can put a little t here, tangential acceleration. Okay, tangential acceleration over the radius is equal to alpha. So now I have two formulas for tau. I have RF, and then I have AT over R. Okay. I want to try to get a formula where F is equal to ma for some effective mass. I'm trying to figure out what this mass should be. Okay, so now what I have is I'm going to divide by R, and I'll have F is equal to IAT over R squared. Right? And then I is equal to 1/2 mr squared, and then I'll have 1/2 mr squared A over R squared, and then the R squareds canceled. I get 1/2 ma. All right, if this step here is confusing you, that does not bother me. This is a little bit complicated. What we did was we're trying to get an effective mass, so the equivalent of how this thing rotates or how the angular acceleration behaves, to make it similar to how a mass would accelerate on a horizontal table. The way I did that, I was looking for a formula where force is equal to acceleration times some effective mass. All right, so I played around with torque is equal to R times F, and then I said torque is also equal to I times alpha, and alpha is the acceleration over the tangential acceleration over the radius. Okay, then I say RF is also equal. RF then is equal to I times A over R, and then I write it in the form I said. I want F is equal to something times the acceleration, and then I end up getting 1/2 m times A. And I use the fact that for a disk, a uniform disk, the moment of inertia is 1/2 mr squared. Okay, so I get that this effective mass is 1/2 m, since F is equal to 1/2 m times A. So now I can pretend that this is just a mass sliding with mass 1/2 m on a horizontal frictionless surface. And now I solve the problem that we solved before, back in probably quiz 3, I would imagine. So I do this snake-like direction, this curved snake-like direction S plus x direction. So remember how we did these Atwood type problems. So there's the only net force in the s direction will be the weight of this hanging object here, which will be m times g. It's in the negative s direction, so F net s is equal to minus mg. Now I'm going to apply Newton's second law to this system of the two blocks. Okay, the whole mass of the system is 1/2 m plus 1/2 capital M plus small m times the acceleration of the whole system, which is as. So that I have the net force S, which I've calculated here. And so this is going to be minus mg. So now I can solve for as. It'll be minus mg divided by the sum, but the total mass, 1/2 m plus small m. And then I get, plugging in the numbers, minus 0.71 for the small mass, small m, 9.8 for g, 1/2 times the capital M, which is 2.15, plus small m, which is 0.71. And then I get that the magnitude of AS, they don't need a sign of anything, they just want magnitude is going to be 3.898 meters per second squared. Now, unfortunately, that's not what they're asking for. They want to know the angular acceleration of the cylinder. So once I know this how fast the acceleration is of the mass, I can now figure out the acceleration, angular acceleration, going back to this formula here. Okay, so here alpha is equal to tangential acceleration over r. So I can get alpha as tangential acceleration, so that's how fast this rim will be spinning. Okay, the point on the rim will be spinning, divided by r, and that's 78 radians per second squared. Okay, so I said this problem is rather difficult. you don't have to worry too much about these steps, but the key steps are torque. So let me try to extract out the concepts you're supposed to be master. Torque is equal to R times F. Torque is equal to I times alpha. And the alpha is related to the tangential acceleration divided by R. So this you should know and should be able to deal with. So in some sense, this stuff you should be on top of. This stuff is maybe a bit complicated. Okay, but if you do this, you can convert this problem into a linear motion problem for this mass, and you get an effective mass of 1/2 m. Then you can solve for the acceleration of this two-mass system by doing this snake-like curved snake-like direction S, and then the net force on this two-mass system is going to be mg going down. That's what I have here. And then the total mass of the system is 1/2 m plus capital M plus small m. And so I can get the acceleration using Newton's second law here, minus mg over 1/2 capital M plus small m. And then I can get the angular acceleration. It's going to be the acceleration divided by r. Okay, and I'll get 70 radians per second squared. As I mentioned in the review, when we talk about accelerations in this Quiz 5 material, we won't be doing much centripetal acceleration. We'll be talking about rigid objects rotating, and so the accelerations we'll be talking about are tangential accelerations. So the tangential acceleration is the angular acceleration times the radius. So the angular acceleration is the tangential acceleration divided by the radius. Okay. Now we go on. Okay, so again, this is a rather difficult problem, but I want you to focus on the pieces of this problem and be on top of all of the pieces, all of the steps. So let me explain. So a teeter-totter has a length capital L is equal to 3.9 meters and a mass m is equal to 57 kilograms. Okay, so then the children of mass m1 is 17 kilograms and m2 is 33 kilograms. They sit at the two ends of the teeter-totter. What is the distance d? Distance r, so that's this distance here from this edge to where this point, this balance point is. The fulcrum is this object, such that the teeter-totter is balanced. Okay, so we want to know this distance r1. This is what they call r2 here. The first step, so again, let me emphasize the key concepts here, that we have a uniform, just a uniform teeter-totter. So the mass of the teeter-totter should be an arrow just going straight downwards because that's the weight. The weight of the object is going straight down. Capital M times G is the weight, but it's right smack dab in the middle of the teeter-totter. Okay, so in other words, this distance would be half of L. That would be L over 2. Right? So let's show you here. The weight of the teeter-totter is placed at the center of mass, okay, right in the middle here. That is a key concept that you're responsible to know how to deal with on the quiz. Okay, so if the distance from here to here is L, this is the rotation point. That's where the thing is balanced, and it's going to teeter-totter on that point. It's going to tip from that point. This distance is what we call R1. Since the total length is L, this R2 is going to be L minus R1. Okay, and now what we're going to do, the key concept here is to find out the torques from all three forces and realize that when it's balanced, the net torque will be 0. So let's first find out the torque due to M1. We have the weight acting here. Okay, so we have the weight, the force is M1 times G. The lever arm distance is R1. The angle between the two, angle between these two vectors is going to be 90 degrees. So the sine of 90 degrees is just 1. So R1 M1G, and it's going counterclockwise. The reason it's counterclockwise is if I have the rotation point here and the force is trying to push down, it's rotating my object counterclockwise. Okay, CCW is counterclockwise. Then we have this force over here. It has the force is M2G, the weight of this mass, times its lever arm distance, which is R2. But later on we can put in R2 is equal to L times R1. Then we have the weight of the teeter-totter material itself, and that's from the center. So this distance from this end to this end, as I said, is L over 2. So this little extra piece will be L over 2 minus R1. So see what I did here? This is going to be L over 2. So then this little piece must be L over 2 minus this distance R1. Okay, so then this is L2 over L2 minus R1. And I multiply, then I'm calculating the torque, so it's the lever arm distance, L over 2 minus R1, times the force, which is capital M times G. And this is also going clockwise because it's trying to rotate the, here's the rotation point, it's trying to make the object rotate clockwise. Okay, clockwise. So now, key concept here is that the net torque must be 0. So I like to do it by saying the sum of the counterclockwise torques is equal to the sum of the clockwise torques. So I have R1 M1G is equal to the sum of the clockwise torques, R2 M2G plus L over 2 minus R1, and capital M times G. Okay. Now, so you can cancel out the G's from the equation, just divide by G everywhere, so you don't have to carry it along. Plug in M1 is 17. You don't know R1, that's what we're solving for. But R2 can be written in terms of L minus R1. Remember, that's what we said up here. R2 is equal to L minus R1. Okay, so I can replace that. And then I have times 33 for M2, and then I have L2 minus R1 times capital M, which is 57. So now I have R1 is the only thing I don't know. Multiply 17 R1. Then I have L is equal to 3.9. And then L over T is 1.95. And so I have things with R1s and things without R1s. Let's combine all the things with R1s. I get 17. I get 33 when it comes to the other side. And then I have 57 when it comes to the other side. 17 plus 33 plus 57 is 107. And then all the things remaining, you get 3.9 times 33 plus 1.95 times 57 is 239.85. And then we can divide by 107, get 2.24 meters. Okay, so this problem was kind of hard, but the concepts here, there's maybe about three concepts here I want to cover. One is we have this teeter-totter. It's uniform. It doesn't really say that, but let's assume that it's going. You can just assume that it's balanced out so that the center mass is in the middle here. Okay. So then the weight is capital M times G, and it's a vector going straight down from the center of mass, whereas the masses for the weights are just where they are. You treat those as point particles. Okay, now we're going to say that we're going to calculate the torque about the rotation point. Here's the rotation point. This distance is R1. This distance is R2, which is L minus R1. This distance ends up being, because this is at the middle of the teeter-totter, which is the distance L over 2. This distance is L over 2 minus R1. So now I can get the torques for tau 1, which is going to be counterclockwise, lever arm distance times the force, and then I can get tau 2, lever arm distance times the force. Okay, this is going to be clockwise, and then I have the torque due to this mass. It's going to be the lever arm distance, L over 2 minus R1, times the force, which is capital M times G. This will be clockwise, trying to go like this. Then the net torque must be 0, so the sum of the counterclockwise torques must equal to the sum of the clockwise torques. Then you plug in everything that you know. The only thing you don't know is R1. We replace R2 by L minus R1. And so then we can solve for R1, and we get 2.24 meters. Okay, going on, number 7. A solid round disk with mass 3 kilograms and radius 0.7 meters is rolling at speed v equals 6.1 meters per second, when it encounters a ramp with slope theta is equal to 8.4 degrees as shown. To what high h will it roll up the ramp before stopping? Okay, this is rolling without slipping. So this is not something too complicated. You should be on top of these steps here, okay? So we have a round disk, I is equal to, the moment of inertia is 1/2 mr squared, solid round disk, uniform disk, okay? The problem really should say solid uniform round disk, but if there's an ambiguity like this on your quiz, You can ask whether it's uniform, and the person supervising will make it clear that it should be uniform. Okay? And this is a key formula as well, that the angular velocity, omega, is v over r. Angular velocity, omega, is v over r, where v is how fast the center is moving. It's the same as the speed of a point on the rim for a rotating object, the rotating circle. The kinetic energy of rotation is 1/2 I omega squared. Okay, so plug in I is 1/2 mr squared, so we get 1/2 times 1/2 mr squared, and then omega becomes v over r v squared. Okay, then the r squared cancels the r squared that we get in the denominator, because this becomes v squared over r squared, and then we get a 4mv squared. So the kinetic energy of rotation is 1/4 mv squared. So now we want the total kinetic energy. This was ROT, this is TOT for total. That's the translational part, that's the regular 1/2 mv squared, plus the kinetic energy of rotation, which we said is 1/4 mv squared. So the total is 3/4 mv squared. So you should know how to do this for any shape. Okay, this is not what I consider too complicated. You use omega as v over r, moment inertia is 1/2 mr squared, and kinetic energy of rotation is 1/2 I omega squared. The translation kinetic energy is 1/2 mv squared. Add them all together, you get 3/4 mv squared. Now we're perfectly set up for conservation of energy. Ki plus ui is equal to kf plus uf, where we use the total kinetic energies here. Okay, we need total kinetic energies for all these things. Okay, and u's are the gravitational potential energy. So the initial total kinetic energy is 3/4 mvi squared, where vi is the initial speed. The initial position, initial height will be y equals to 0, so mg1 is 0. The final speed is when it stops, so v final is equal to 0. Okay, and then we have the y final is the final height, so the mgy final for the potential energy. Okay, so now these are 0, so we have 3/4 mvi squared is equal to mgyf, and then I've already removed, there was an m here that I've already removed. Okay, I've canceled them out, they drop out, and I've got 3/4 vi squared g v final. Okay, so now I can solve for v final, and now I can solve for y final. It's 3/4 vi squared divided by g. Plugging in v initial, 6.1, I get 3/4 6.1 squared divided by 9.8, you get 2.85 meters. Okay, to review, there's two concepts here. One is figuring out the kinetic energy of rotation. 1/2 I omega squared. Plug in I is 1/2 mr squared for a solid disk. Plug that in here. I'm going to try to write this in terms of something times mv squared. Okay, and omega has to be written as v over r. So I have the omega squared becomes v squared over r squared, and the r squareds cancel, and you have 1/4 mv squared. So that the total kinetic energy is 1/2 mv squared plus 1/4 mv squared. Translational, rotational. So I get a total of 3/4 mv squared. Okay. Now it's conservation of energy. It starts with only kinetic energy. It starts from ground y equals to 0. Okay, and so I have 3/4 mvi squared plus the initial potential energy, since y is equal to 0. I get 0 here. And then the final kinetic energy is 0 because it stopped moving. And then we have a final height y final. So I get mgy final. Okay, so then I have 3/4 m. There was an m here and there was an m there. Okay, mvi squared is equal to mgy final. And then I just cancel the m's, and you can solve for the y final, and you end up getting that it's 2.85 meters. Okay. Next question. You look at a clock which is mounted to a wall. All right. In which direction does the angular momentum vector of the minute hand point? Okay, so you're looking at this clock. Here's the clock face as you see it, and the clock is going obviously clockwise because it's a clock. So omega is going this way, And so if I want to know by the spin around right hand rule which way omega is going, you cup your fingers so that it's going in the direction of the spinning. Okay, not this way, that would be opposite. You have to go this way. And so you stick out your thumb, and it's going into the page. So you can say into the page, but that's not the way they're describing it here. Remember, we're looking at the clock, so it's going like this, which would be into the page or away from you, okay? Because we're looking at this clock, it's pointing away from you, so that's what they want. It's away from you, or they say into the wall, I guess. Okay? Into the wall. Into the wall that the clock is hanging on. Okay, number 9. So, by the way, so number 8 is clearly an application of the spin around right hand rule. So, spin around, stick your thumb in the direction it goes. The angular momentum is I times omega, so it points in the same direction as omega. Okay, they're all the same in terms of directions. Next problem. Force is 12J newtons applied to a large merry-go-round where R is minus 3I hat minus 1J hat. Okay, so the force is 12J hat. Where the coordinate origin is the center of the merry-go-round, that's the rotation point. So 0, 0, 0 is the rotation point. So what is the torque on the merry-go-round about its center? Okay, so we just want torque is equal to R cross F. And so R, the components of R is minus 3, minus 1, 0. F is 0, 12, 0. You can then go to your equation sheet, which has a formula for the components of the cross product, but we'll use this little table trick that I showed you. You write the components of the first vector, so you write minus 3, minus 1, 0, 0, 12, 0. And then for the x component, you strike out the x row, all this. You take the product of the diagonals, the going downward to the right, minus the product of the off diagonals. Minus 1 times 0, minus 0 times 12, so you just end up with 0 for the x component. For the y component, you strike the middle column, and then you have a gap between these two columns, so you cycle this guy on over to the other side. You get a minus 3, 0 on this side. Okay. Now you look at this little 2x2 table. You multiply the diagonals, going downward to the right, 0 times 0, minus 3 times 0, so you end up getting 0 again. Okay, now for tz, we write this table, we strike out the third column, and then take the product of these diagonals, so going downward right, minus 3 times plus 12, okay, minus the product of minus 1 times 0. So I get minus 36 newton meters. Okay, so now the only thing that's non-zero is tau z, negative 36 newton meters. So tau, in terms of components, is 0, 0, minus 36 newton meters. So it's minus 36 newton meters k hat. Okay, so here the concept is just simply torque is r cross f, lever arm vector or position vector cross f. Then you take the component formula. You can use these table formulas that I've taught you, or you can just use the formulas that are written out in the equation sheet. Let's go on to the last problem. Number 10, a person is sitting at rest on a frictionless stool while holding a frictionless spinning wheel. The axle of the wheel is vertical, and the z component of the angular momentum of the wheel is minus Lw. The person then flips the spinning wheel upside down. We actually did this as a demo today, so that the angular momentum vector points upward instead of downwards. The wheel continues to spin at the same rate. After the wheel is spun, the final angular momentum of the person and stool, but not including the wheel, along the z-axis is what? Okay, so if you didn't understand that, read the problem again. You have the wheel, it's spinning, so it's pointing down. The angular momentum is pointing down. Then you make it point up without changing the angular speed. So the question is, how fast are you and the stool spinning in terms of the angular, the final angular momentum of you and the stool, of the person in the stool, actually. Okay, we have angular momentum conservation. Li total, L initial total is equal to L final total. That's a key concept. So that's the initial angular momentum of the wheel plus the initial angular momentum of the person and with stool. And then we have the final angular momentum of the wheel plus the final angular momentum of the person plus stool. Now the wheel starts off with minus L omega, or L W actually, that's the W. W for wheel. Okay, so then the initial angular momentum of the person's stool is 0 because the person's sitting at rest, the stool is at rest. And now for L final wheel, we have plus LW. It should be W actually, not omega. Okay? So, because we're told that it flips to positive LW. And then we have the unknown final angular momentum of the person plus the stool. But this must equal that by angular momentum conservation. And so I bring this to the other side. I get L final for the person plus stool is minus 2L W. Okay? So the key concept here is angular momentum conservation. And then knowing that the initial angular momentum equals the final angular momentum, we have the piece from the wheel and the person and the stool. And then we have the final angular momentum for the wheel and final angular momentum for the person and the stool. So we can then easily solve for the final angular momentum of the person and the stool. And it ends up being negative 2 times LW. All right, if you have any questions, please email me. I will put up some additional videos as well with further practice problems later.